Hi everyone. I will be presenting joint work with Mirza, Baig, Alessia, Milani, and Corentin Travers about long-list snapshots with polylogarithmic amortized step complexity. Please feel free to stop me if you have any questions. We consider a standard shared memory model in which n-deterministic processes with unique IDs communicate via shared memory using atomic read and write operations. Processes may fail stop, but this must not prevent other processes from making progress. So we consider non-blocking progress conditions that preclude the use of locks. An algorithm is said to be wait-free if every operation completes in a finite number of its own read-write steps. It is lock-free if whenever processes take more and more steps, some operation terminates. And it is obstruction-free if it is guaranteed that a process terminates its operation if it runs solo long enough. And the correctness conditions we assume is the standard linearizability condition. So we investigate in this work the well-studied snapshot object. The snapshot abstraction was invented at the early 90s independently by Afek et al., Anderson, and Aspenes and Herlihy. The abstract state of an atomic snapshot is an array with n components, where n is the number of processes sharing the implementation. A single writer snapshot supports two operations. An update operation by process I changes the value of the ith component of the snapshot. So in this case, this is the second component for process P2. And a scan operation returns an atomic view, which is a vector consisting of all the component values as they existed at some point in time during the execution of the scan. Now, what do we know about the step complexity of implementing snapshots? Well, we know that there exist implementations of multi-writer snapshots with linear worst-case step complexity. And we also know that we cannot do better in terms of worst-case operation step complexity. And this was proven long ago by Jayanthi, Tan, and Tueg for a large class of objects called perturbable objects that include snapshot. They show that for any non-blocking implementation of such objects, even obstruction-free implementations, there is an execution in which some operation can be made to perform a linear number of steps. And single writer snapshots, as I said, belong to this set of objects. So it seems that the problem was settled, but then 15 years later, Aspenes, Satya, and Senzorilel observed that the lower bound of Jayanthi, Tan, and Tueg holds only for executions in which the number of operations applied to the object is exponential in n. They leverage this observation to construct counters and additional objects for which worst-case step complexity is polylogarithmic in the length of the execution. By building on these results and extending them, Aspenes, Satya, Senzorilel, and Ellen have shown a similar result for snapshots. More specifically, they presented the implementation of a B-limited use snapshot in which the complexity of operations is polylogarithmic in B, where B is the bound on the snapshot, or in other words, it is the maximum number of update operations supported by the snapshot algorithm. However, as the length of the execution grows, the step complexity grows as well, and when the length of the execution becomes exponential, operation complexity once again becomes linear, as well as the amortized step complexity, which is the average step complexity of all operations that appear in the execution. So now the lower bound of Jayanthi, Tan, and Tueg does not preclude algorithms that have sublinear amortized step complexity. However, all known snapshot algorithms prior to this work have linear amortized step complexity in very long executions. And so the question is, can we improve on this? And that's a question that we address in this work. So we present the first non-blocking snapshot algorithm that has sublinear amortized step complexity in all executions regardless of the length and not just in short ones. Specifically, we present a weight-free single writer snapshot algorithm whose amortized step complexity is O of log n cubed, which is an exponential improvement in comparison to previous algorithms. Now, our algorithm improves on the snapshot algorithm of Asynchronous et al. By constructing a novel two-component max array that has log square amortized step complexity in all executions under an assumption I'll describe soon. So the snapshot algorithm of Asynchronous et al. Encapsulate two types of objects, max registers and a new object type they defined and implemented, which is called the two-component max array, which encapsulate max registers as well. So next I will tell you what max registers and max arrays are. A max register defined by Asynchronous and Sensor Hillel stores integer values. It supports two operations. The write max operation writes a new value, and the read max operation returns the largest value written by a write max operation linearized before it. In the algorithm they presented, both operation types incur log of v step complexity, where v is the value of the register when the operation is applied to it. But when the register's values grows more and more and becomes exponential in n, this complexity can become superlinear, in which case the algorithm is able to fall back to an ON steps snapshot implementation, a linear time snapshot implementation. So like they do, we also denote in our work and in this presentation by max m, a max register that can only assume values, integer values between 0 and m minus 1. In recent work, Baig et al. Presented the first weight-free unbounded max register. That is a max register that can assume any non-negative integer value, which has amortized step complexity logarithmic in n in all executions, regardless of the length. But this is only guaranteed in executions in which no write max operation increases the value of the register by more than n, a requirement called the n-bounded increment assumption. This assumption is satisfied by the counter construction of Asynchronous et al., which allowed Baig et al. To derive the first counter with polylogarithmic amortized space complexity. The key technical tool developed by Asynchronous, Sensor Hillel, and Ellen for their snapshot algorithm is the two-component max array object. Essentially, this is a two-component snapshot where each component is a max register rather than a simple register. We call these two components the left and the right components. And the object supports two operations. A max update operation invokes the write max operation, a max update operation invokes the write max operation on either the left or the right component, depending on the first parameter, that is the side parameter, with argument v. And it has operation step complexity of O of log m, where m is the bound on the max registers. The max scan operation returns an atomic view of the two components. When the values of both max components is bounded by m, the worst case step complexity of max update, as I said, is logarithmic in m, but that of max scan is higher, it's O of log m squared. However, this complexity may grow also here beyond any bound as m is being increased. So returning to the schematic view of the snapshot object implementation by Asynchronous et al., recall that it uses both max registers and two-component max arrays, which in turn encapsulate max registers. To obtain a snapshot algorithm with polylogarithmic amortized step complexity, we retain the snapshot algorithm of Asynchronous et al., but we replace the object which it encapsulates. So we replace the bounded max register used by the algorithm by the unbounded max register of Baig et al. That has logarithmic amortized state complexity. And we replace their two-component max array, bounded max array, with a novel implementation of a polylogarithmic amortized step complexity max array, which is our key technical contribution in this work. So now let's finally get to see the new algorithm, which is quite short, so I can explain all details. So the new algorithm uses the following data structures. MRL and MRR are two unbounded max registers, such as those implemented by Baig et al. MRL is written to by max update operations applied to the left component, and MR right is written to by max update operations applied to the right component. In addition, the algorithm uses an unbounded number of two-component max arrays, denoted MA0, MA1, MA2, etc., where both components are M-bounded, as implemented by Aspanes et al. And we set M equals N squared for reasons that will become clearer soon. The max registers and both components of all max arrays are all initialized to 0. The algorithm uses a helping mechanism in which operations attempt to help concurrent max scan operations to complete. This mechanism uses an array of single writer registers called H, where process I helps by writing to entry H of I. Each such entry contains a local timestamp of the helping process and a view computed by that process, as we will explain soon. Before presenting the algorithm, let's define the following notation. At any point in the execution, there is a single active max array, which is the one with the largest index that was written to in the course of the execution, either to the left side or to the right side or to both. In the scenario we'll soon see, this is the max array indexed by H. As we prove in the paper, the following representation invariant of the algorithms are maintained. The left and the right components of the active max array, respectively, store the log m least significant bits of the value written by the last linearized maxed update operation on the respective component of the implemented max array. Okay, so the active bounded array, the active two-component bounded array stores the least significant bits of the left and right most updated or largest values of the implemented object. Now, let I1 and I2 respectively denote the high order bits of the last values written to the left, or the maximum values written to the left and right components respectively. Then H, the index of the active max array, is their sum. As we prove, since I1 and I2 are monotonically increasing because these are max registers, so is H. And moreover, each index H corresponds to a unique pair of such indexes I1 and I2. Thus, given H, I1 and I2 are determined, and the value of the implemented max array is as written here. The log M LSB, the significant bits of each component, are stored at the respective component of the active bounded max array, whereas the rest of the bit, the high order bits, are represented by I1 and I2, depending on whether this is the left or the right component. Now let's see how the max scan operation by process I works. It consists of an infinite loop, where in each iteration, process I attempts to obtain a view of the most significant bits of the left and right unbounded max registers. So the right max register is red, then the left max register is red, and then the right max register is being read again. So these two unbounded max registers. Now, if the most significant bits of R1 and R2 are the same, then we know that the most significant bits of both the left and right components were I1 and I2, as computed here, when the left max register was read. So the index of the active array is the sum, that is I1 plus I2, which we denote by H. Next, process I writes the log m low order bits to the max array with index H, and then invokes a max scan operation on it, obtaining some view L prime R prime. Finally, process I verifies that the active max array is still H by reading the pair of unbounded max registers once again, and checking that the values of the most significant bits did not change. If this is indeed the case, then as we prove, the max can obtain the view of the least significant bits, and I1 and I2 are a view of the most significant bits at the time when the max scan here is linearized. Thus, a view can be constructed by concatenating the high order and low order bits of the left and right values, read, and process I proceeds to help and return the view. And helping is done simply by writing to entry I of the helping array a monotonically increasing timestamp of process I and the view itself. So here is where we actually concatenate the low order bits and the high order bits to construct the view returned here. In the scenario we just saw, process I succeeds in one of its loop iterations to compute a view by itself. However, this may never happen if concurrent max update operations keep occurring and the index of the active bounded max array keeps growing. This is where the helping mechanism comes to the rescue. Once every theta of n steps performed by the max scan operation, it collects the value in the helping array, H. If the timestamp in one of its entries grows by at least 2, then we know that the view stored in that entry was computed in its entirety within the time interval of I scan operation, so I terminates by returning the view. Finally, the max update operation is very simple. It invokes a the max update operation is very simple. It invokes a write max operation on either the left or the right unbounded max registers, depending on the side parameter, to write the value V passed as the second parameter. And then it invokes a max scan operation in order to ensure that it is linearized before termination, and also in order to help concurrent max scan operations, if any. It disregards the value returned by the max scan procedure. As we prove, the following linearization point exists. Max scan operations that succeed in computing a view and return here are linearized when they invoke the max scan operation on the active bounded max array just before returning. A max scan that returns a value read from an entry of the helping array, say entry J, is linearized when the corresponding helping operation by process J was linearized. The definition of the linearization points of max updates is slightly more complicated. Assume without loss of generality that a max update operation U writes to the left unbounded max register. Then it is linearized at the first time when some operation, possibly U itself, reads that max register, that is the left max register after U writes to it, and then performs a max update on the left side of a bounded max register, and that is the point of linearization. So observe that several max update operations may be linearized at the same point, in which case they are ordered according to the order they wrote to the left unbounded max registers, and obviously the same logic, the same rule of linearization applies to updates to the right side. So it's not difficult to see that the algorithm is weight-free. What we need to show is that the loop of every max scan operation cannot continue taking steps indefinitely. This is done by using the following observation. An iteration can only fail if the most significant bits of either the left or the right components change. However, since we assume that the execution satisfies the n-bounded increment assumption, and since m equals n squared, every 2 iterations that are performed by the max scan operation, 2 iterations of the loop, a linear number of max update operations by other processes are performed. So after a constant number of iterations, some other process J updates its entry of the helping array at most twice, and so the max scan operation will be able to return the view computed by J. As for amortized step complexity, each increment of the most significant bits of either the left or the right side increases the index of the active bounded array, and this causes at most n-1 unsuccessful loop iterations, at most 1 for each other process. These can be amortized against the at least n max update operations that are performed on each bounded max arrays, again because both components are bounded by m, which equals n squared. As for the rest of the operations performed by maxscan, the dominant complexity factor is that of the max update operations, which incurs O log of n squared worst case step complexity, and doing the calculation establishes an amortized step complexity of log n squared. You can find the details in the paper. Thus, the new algorithm is a linearizable weight-free 2-component max array implementation with O of log n squared amortized step complexity. Let's not forget that our goal is a snapshot algorithm. And as I've mentioned previously, we use the snapshot algorithm of Asynchronous et al. And replace their bounded max array with the unbounded max array of Baig et al. These are the max arrays. We replace them with the constructions we have just shown. And they also use a max register, which we replaced by the max register of Baig et al. From DISC last year. I won't have time to describe the snapshot algorithm of Asynchronous et al. In detail, whose data representation is depicted below, but only to mention that each update operation supply a logarithmic number of max scan and max update operations on 2-component max array on a path from a leaf to the root of the tree. So this gives us an extra log n factor, which brings the complexity from O of log n squared to O of log n cube amortized step complexity. And once again, you can see the details in the paper. One more important detail I should mention is that it's easy to see that in this construction, the n-bounded increment assumption is indeed satisfied. So before terminating, let me describe briefly some more relevant work. Atiyah and Hendler showed that any snapshot implementation from read and write, as well as compare and swap, has an execution consisting of a linear number of operations in which the average state complexity is logarithmic, which means that our upper bound is not far from being tight. And last but certainly not least, the most relevant related work to our work is that of Aspenes and Cesar Hillel that present a randomized limited use snapshot with log cube amortized worst case step complexity. So, sorry, not amortized, but expected worst case step complexity. And in order to do so, they also implement an unbounded 2-component max array. This work was published in DISC 2013, but an extended technical report by the same authors contains a different implementation of the two-component max array, which inspired our algorithm. Our algorithm uses the same representation of array components as theirs. The key differences are that we employ deterministic helping mechanism, whereas they use a randomized mechanism. Hence, we obtain polylogarithmic amortized step complexity, whereas they obtain polylogarithmic expected worst case step complexity. Another difference is that the extra check that the active bounded buffer did not change that we have added to our algorithm after the scan of that buffer makes our linearizability proofs much simpler since explicit linearization points can be identified. So to conclude, there are also some interesting avenues for future research. One of them is obviously to find the tight bound for snapshot. So currently we have an O of log n cube amortized step complexity and the lower bound of only log, and we don't know what the tight bound is. And a related question is the bound for two-component max array. Is it tight? Also here, there is a gap between log square and log, which is the lower bound for two-component max array. And with this, I conclude, and I will meet you in the Zoom of PODC, and let's hope the next PODC will be frontal and not virtual. So, bye for now.